Okay, let's go over the probability question I did um a couple of days ago. So inside here we have question 8. In part A, we're asked, you have six weighted dice. Die I has probability one half turning up that I number, and then equal chances of coming up with any other number. You pick a die at random uniformly and roll it twice. Let X and Y be the outcome of the two rows. Are X and Y independent? Explain your answer. So intuitively, if we think about this question, like if we know that X, like the row of X, then we kind of have more idea of what Y is. So in that sense, we probably know that it's not independent. If we were to show that it's the case, we kind of can just set X to be equal to 1 and Y equal to be 1, right? And then we just want to show that like P of X equals X and Y equal to Y is not equal to P of X equal to X times P of Y equal to Y. So this is like the typical independence equation. We're just going to show that it doesn't hold here. So when we're trying to show that, we're just kind of going to calculate each of the pieces independently and then just putting it together. So for first, we're going to find the marginal probability of P of X equals 1 using the law of total probability. We can just say that P of X equal to 1 is the sum from K equal to 1 to up to 6 of P of X equal to 1, conditioned on the fact of die K times the probability of die K, right? Because we can get either the row of 1, 2, 3, 4, 5, 6, either of one of those die, and then the probability would be dependent on that. So if it was a one, then we would just split that into one case, and then for all the other five dice, it doesn't matter which one we get, and it would be another case, right? So we just split it up, and getting each one would be having probability 1/6. So then we know that inside here in this condition, if it was die one, then we would have one half chance, and if it wasn't, then it would be 1/10 of a chance. And then here, because there were five dice, we would have five over here. So that's how we get 1/6 as our kind of marginal probability. And since it's symmetric, since X and Y are like the same, then P of Y equal 1 is also 1/6. So P of X equal to 1 times P of Y equal to 1 would be 1 over 36. But however, when we look at P of X equal 1 and Y equal 1, we just kind of do the same thing by law of total probability, conditioning it on the die K. P of X equal 1 condition on given that die K, P of Y equal 1 given die K, times the probability of getting that die. Inside here, we would have 1/6, and then it would be 1/2 squared times 5 over 1/10 squared, which we get 1 over 20. So inside here, the two things are not equal, so they're not independent. It's important that you kind of use this condition to show that it doesn't work. In the second part, let's move on. We have if X is equal to 1, what is the conditional probability that you have selected dial 1? Okay, so this is just putting it together like with what we just calculated using Bayes' theorem. I think it's pretty straightforward. By Bayes' theorem, we're just asked, given X is equal to 1, what is the probability that we have die 1, right? So then we can just write on the denominator it's P equals X equal to 1. On the top, we have X equal 1 given die 1 times the probability of getting die 1. We already calculated these part in the earlier part, so we just put it in and we get 1/2. Okay, moving on. Actually, this question, like part A is kind of just part A and part B is just kind of part B. So it's kind of like two kind of questions, separate questions, just combined into one bigger one. So in part B, we're given kind of like, it's kind of testing generating functions. So we have a single bacterium growing on a dish, either divides into two identical offsprings after 1 hour, a fission event, or else it dies at that time. The probability of fission is P from between 0 and 1/2, and the probability of dying is 1 minus that. Each live offspring behaves the same way independently of all the others dividing or dying after 1 hour. Okay, so basically this is just like a typical branching thing, right? We have two scenarios. Either living, we switch, let's me switch a pen. either living, which is um, either dying or living, which basically, if it dies, then it's zero. If it lives, then and divides, it's two. Um, okay, so we're given that the probability of dying is Q. This is Q and this is P, and P plus Q is equal to 1 because these are the two scenarios, right? Yeah. Okay, so in part one, let AI, this alpha one, be the probability that the size of a colony eventually reaches zero. So it's the extinction probability, given that it starts with exactly I bacteria. Using the law of total probability show that this is true. Deduce that with probability one, the size of the colony eventually reaches zero, no matter what the initial size. So we want to show this equation and just show that it will always become extinct. So the idea behind this is kind of like we just walk through like typical things and reason about what we know. So we can kind of think of it as this way. Um, Suppose we have I like I bacteria. And that means that it's kind of like they all each have their own lineages, right? The only way that we can be extinct is when we have nothing left, everything dies out. So all of the branches have to die out independently. So what this means is that for alpha I, the probability that the I, like with I population that dies out is for each one to be dying out. So it would just be alpha 1 to the I power because each one has to die, each of the lineages have to die independently, right? So that's kind of like the main relationship we have here. So if it was 2 in our scenario, then alpha 2 would just be alpha 1 squared. And next, what we know is we kind of can break down what we need based on the first hour, because that's kind of what we know, right? In the first scenario, it either lives or dies. If it dies with probability 1 minus p, then we have 0 bacteria left. And if it divides with probability p, then we have 2 bacteria. So then our alpha 1, so the probability that it kind of dies out with 1 bacteria is equal to 1 minus p of alpha 0 plus p of alpha 2, right? That's just the classic definition of law of total probability. And then we can kind of simplify this a bit further because we know that since if there's nothing, no one in the population, then by all means it's one, right? It's extinct already. And earlier we just said that alpha 2 is equal to alpha 1 squared. We just showed that. So that's kind of the relationship we put in. And we get to this. And then next we just rearrange this into the classic quadratic form. And then we factor it so that we get to this form. So now we can kind of see that from this factored form, there are two roots. Either alpha 1 is equal to 1 or that it's equal to 1 minus p divided by p. But we see that the second root is actually extraneous because it's not possible that we have this, because we have a condition that we haven't used. P has to be from 0 to 1 half. So 1 minus p has to be greater than 1 half. But then that would mean that the numerator is larger than the denominator. So then we have a problem that it's greater than 1. But the extinct probability can only be as great as from 0 to 1. So then that's just extraneous root that we have to discard. So then that means that we have shown that alpha 1 is equal to 1. So then the population will die out eventually. Okay, moving on to part two. Since the size of the colony must eventually reach zero, the total number n represents the number of fission event is finite. Let g of ns be its probability generating function. Show that g of ns is equal to that thing, and so compute this thing. Okay, so this is again using law of total probability. We kind of just condition on what we know on the first hour because we see that Q and this thing, we kind of know, okay, yeah, we're gonna have to condition it on the two things. And since n is finite, we can kind of work around what we know. Let's dive in. So we know that this is kind of like the typical definition of what a generating function is, right? G of ns is equal to the expectation of s to the nth power and Rn is the number of fission events. So conditioning on the first event, if the first bacteria dies n equal to 0, and it occurs with probability q, So then it would just be Q times S to the zero because it dies, right? N is equal to zero. And then otherwise, we know that there would be one fission event and two lineages because we have two offsprings. And the two offsprings are each kind of like their own independent thing, right? So then with probability P, we have the expectation of S. And then we have one fission plus whatever how many fissions the first offspring has and the second offspring has. So N1 plus N2. So then we can just rewrite our G of N into this form, right? The sum of those two. And then next we know that N1 and N2 has the same distribution as N because it's the same thing, right? We just have one thing and then it has its own lineages. So we can rewrite E of S of this thing has just first extracting because each one in the exponent would just be multiplied together. So it would just be S times E of S to the N minus N1 times E of S to the N2. And then because each of them are the same distribution, we can just write with the same generating function. So it would be S times G of NS squared. So then we can put this back into our equation and it looks much nicer to the form that we need. Next, we're asked to solve it. So then we just arrange it into the normal form of a quadratic equation. Then we just solve it using the quadratic formula and we get this. And there are actually two roots to this. And there's a positive one and there's a negative one. And we're not sure which one to use, so we just kind of check the boundary condition. When S is equal to zero, we know that P of N equal to zero, so that's the probability of Q, right? And then it means that after testing, we have the negative root works out and converges to that answer, whereas the positive root doesn't. So that's why we just pick our answer to be the negative root. Okay, moving on. Part three. Using G of NS or otherwise calculate the expected value of N. The minute you see otherwise, you know you have to use G of NS. And we know this is a classic property we know already that we use so much. It's like the expected value would just be the derivative of G of N when S is equal to 1, right? So we're gonna just try to find that. And here it's in my actual like first attempt at the question, I kind of wrote out with the full equation of using PQS and thus taking the derivative of that, which was very calculation heavy. And I made probably some kind of error in my derivatives calculation because the answer wasn't exactly the nice form that we got. So I think the major thing here is kind of keeping track of what the equations using the generating function rather than the actual PS like PQS. Like that saves a lot of like error prone things. That just saves a lot of trouble. So we know that this is the case. Mm. We have our earlier equation. We just take the derivative of that. This is the classic multiplication rule, and the constant was canceled out because it was taken. And when s is equal to 1, we know that g of n of 1 would just be the sum of the probabilities from k equal to 0 all the way to infinity. And since we know that n is finite, so the sum of this has to be equal to 1 from the earlier part. So hence g of n of 1 is equal to 1. So then that makes our calculation much simpler when we put back s equal to 1 and g of n equal to 1. We get this expression. We just substitute g prime, like the derivative of g of n as e of n. So then we get to this point. And then this is just rearranging and we get e of n is equal to p divided by 1 minus 2p. And it's a very nice form and it's there's barely any calculation. It's very straightforward. I think that's the major takeaway from part three is that like don't go into like the full algebra bash of finding what g of n is and plugging that into this expression and then taking the derivative of that. Things could go quite wrong and it indeed happened for me. So that's something to watch out for. Okay, that takes me to the end of this question. I think the major things that this tested for was the question part A was just testing for if you know the law of total probability and if you kind of know conditional probability, like the Bayes theorem and independence. And part B was more testing on generating functions and kind of branching processes. Cool, let's end off here.